Okay, so last time we were taking a look at falling objects. And we ended up with the differential equation. So we had v was vertical velocity. And v was, of course, the derivative of height with respect to time. So this is just height. And of course, a was v prime. Where a is acceleration, vertical acceleration. The usual thing where we have a is v prime and v is h prime, or whatever letter you're using for height. And we ended up with the following differential equation. So v prime equals, v prime plus c2v plus g equals 0. Yep, sorry. No vector symbols over the v. I just finished another class where there are vector symbols over everything. And of course, we can go ahead and write this as v prime equals minus c2v minus g. And we saw that we could sketch a slope field for this thing. So I put t along this axis, time, and I can put v along this axis. And that's velocity. And we saw that we have, let's see, at minus g over c2, we have these horizontal lines, and then over here we have line above that, we have lines with negative slope. The further you go up, the more negative the slope becomes. And then above that, we have lines with positive slope. And so on. And the idea, of course, is that if I have a curve which starts with some particular velocity, that velocity eventually reaches, it gets closer and closer to this terminal velocity. Here's our terminal velocity. And I said we couldn't solve this using the techniques in this course. Actually, I'm wrong. We could play exactly the same game with this that we did when we were doing Newton's law of cooling. We could change variables again, and which was the trick we were doing with Newton's law of cooling. But I'm not going to do that. Instead, I want to take a look at a way of approximating solutions to differential equations when you cannot solve them analytically. How can we approximate solutions to first order differential equations? So remember, first order means that the highest order derivative is 1. When we write this in terms of v, the highest order derivative is just the first derivative. So when solving them analytically, using calculus, using the the integration, rules that you learned in calculus, is difficult or impossible. So how do you approximate these curves when finding them the exact curve analytically, which is sometimes possible, but in cases where it's difficult or impossible, or when you're using a computer to approximate the curves and the computer doesn't have, can't do calculus. So the idea is that these curves basically follow these little slope lines, that you start somewhere and they follow the slope lines, and that's basically the whole idea. So if we're going to approximate these, what you do is you artificially put a mesh on time, break it up into little parts. Now we are already experienced where the mesh has been imposed by somebody else, and this time we're going to impose the mesh ourselves. So the idea is to artificially make time discrete, which is basically, it's always an artificial process, almost always. Artificially make time discrete. So let's pick some numbers to put in for C and C2 and G. Let's say G, on the surface of the, near the surface of the Earth, the acceleration due to gravity is about 9.8 meters per second. Let's say G is 10. We'll just round 9.8 to 10. Sorry, meters per second squared. And C2, let's pick something pretty easy. How about 1? By the way, what are the units for C2?
It would be per second.
Right, exactly. If that's not clear to everybody, so this is second to the, basically second to the minus 1. If that's not clear to everybody, notice that we have sort of 3 terms here or 3 terms here. When you're adding or subtracting things, they all have to have the same units. All 3 of these things have to have the same units. We already know that G is in meters per second squared, which makes sense with the derivative of velocity. Derivative of velocity is going to be an acceleration, so acceleration is going to be in a unit of distance divided by a unit of time squared. We've already used meters and seconds for our units of distance and time respectively. So this term has to be in terms of meters per second squared also. Now, velocity, if we're measuring distance in meters and this in seconds, this is going to be in meters per second. So for this whole term to be in meters per second squared, this has to be 1 over seconds. 1 over seconds times meters per second is meters per second squared. So s to the minus 1 or 1 over s if you like. So that gives us a differential equation to start with. Where we don't have to worry about letters for our constants. So we have v prime equals minus 1 times v minus 10. I'm not writing units this time. It'd be pretty weird to write units when I'm writing it out this way. So I've just put 1 in for C2, and I put 10 in for G. And let's get an initial velocity. Say we're dropping this thing. We won't give it an initial upwards or downwards velocity. So v at time 0 is equal to 0. Our up and down velocity at time 0 will be 0. So this is my v at time 0 will be 0 meters per second. So this is my initial condition. Here's my differential equation, first order differential equation. So when I give you a differential equation and initial conditions, I've given you what's called an initial value problem. We've seen tons and tons of discrete initial value problems in this course. Here's a differential equation initial value problem. And we could go ahead and solve this analytically. We actually do have the tools. I'd have to change from v to some artificial, some artificial variable that I would, would be like q equals v plus 10 and plug that in, right? And I could go ahead and solve it that way. But let's not do that. Instead, let's take time and break it up into discrete parts. So I'm looking for a curve or approximation to a curve that satisfies this initial value problem. When t equals 0, v equals 0. So I know the curve goes through this point 0, 0. Let's see. T equals 1 second, t equals 2 seconds, t equals 3 seconds, t equals 4 seconds, 5, and this axis, this is in seconds, v is in meters per second. Now we have to make a decision as to how to make time discrete, how finely we chop up time. Let's just chop up time into 1 second intervals. So this is an arbitrary decision. Break time into 1 second intervals. What I've just decided is how fine my mesh is going to be. I'm going to chop time, which is a continuous variable, up into 1 second cells. So this is, I've just decided how fine my mesh is. Now I just made an arbitrary decision to break it up into 1 second intervals. So I know my curve looks something like this, and it's eventually going to level out at g divided by c2. In other words, it's going to level out at height minus 10. I know that that's really what's going to happen if I take this object and drop it. Instead, let's just do this 1 second at a time. I know we start at this point, at the point t equals 0, v equals 0. Where am I after 1 second? So approximately. So I start off at t equals 0, I'm at v equals 0. That's my initial condition. Let's see where I am 1 second later. Well, at t equals 0, what is uh-oh. Okay, I can see I didn't chop up time finely enough. Yep, that's bad on my part. Okay, sorry. My decision to break time into 1 second intervals was dumb. I'm going to break time up into 1/10 second intervals. So this is 0.1, this is 0.2, 0.3, 0.4, 0.5. So at t equals 0.1, sorry about that. At t equals 0.1, let's figure out where we are. So at t equals 0, what's my slope? So if you plug in t equals 0, what do you get for v prime? Just go ahead. This tells you what you get for v prime at t equals 0. So remember, our velocity at t equals 0 was v equals 0. T equals 0, v equals 0. So if you plug in v equals 0, what do you get for your v prime?
10.
10?
I mean, negative 10.
Right. So you get negative 10. Your v prime equals negative 10. So if I start off at height 0, I go 1/10 of a unit over at slope minus 10. How far down am I? So at t equals 0.1, so I start off at 0, at height 0. I go over by 0.1 unit, and I'm going down with slope minus 10. How far do I go down?
By 1.
By 1. So the slope of this line equals minus 10. Where did I get the minus 10? Well, at t equals 0, I was at velocity 0. I was just dropping this thing. I plug that in, I get minus 10. I plug that into my slope equation. I get minus 10. If you start at height 0 and go over with slope minus 10 for 0.1 units, you get minus 1. So after 1/10 of a second, I'm falling with speed of 1 meter per second, according to what I've computed so far. Now let's figure out, so let's see, my velocity is going to be minus 1. I'm dropping at 1 unit per second, 1 meter per second. So minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10. Let's figure out where we are after 2/10 of a second. So at 1/10 of a second, my velocity at t equals 0.1, my velocity, according to what I've computed so far, is minus 1. if I find out what b prime is at t equals 0.1, I'm going to plug in b equals -1 into that equation up there. So -1 minus 10. I just put my velocity equal -1 into this equation, which gives me v prime. Minus 1 is 1, minus 10 is equal to -9. So 1 minus 10 is -9. So my slope here is -9. So if I'm starting off at height -1, I go over 1/10 of a unit with slope -9. How high am I after 2/10 of a second? So you start off at height -1.
Negative 2.8.
Nope. Because I'm only moving 1 more tenth of a second over.
Yeah, but it would be the speed that you would gain, which would be the acceleration times the time. But
No, you're overthinking it. So you start off at height -1. You go over 1/10 of a unit, another 1/10 of a unit, and your slope is -9. It was -10 over here, now it's -9. So it's not as steep as it was before. So if you go over 1/10 of a unit at slope -9, how much more do you drop?
it'd be negative 1.9.
Right, you'd be at height -1.9. So each of these is 1/10 of a unit. So 0.1, 0.1, 0.1. The first time you're dropping at slope 10. Now you're dropping at slope 9. So if this is 0.1 unit and you're dropping at slope 9, that means the amount you've dropped is 0.9, is 0.1 times times -9. And if you start off at height -1, you go down to -1.9. I think I might be making this harder than I intend to, because it seems like this is not as clear to you as I want it to be.
I understood what I went. I accidentally put in 0.2 instead of just 0.1.
No, I understand, but I'm speaking to everybody. I think just judging by the looks on the faces I can see, this isn't as clear as I want it to be. Let's do another one. So now we're at height -1.9. I want to now go over and figure out where we are at time 0.3. So I'm at height -1.9. I'm going to move over another 1/10 of a unit, 0.1. Let's figure out what slope I'm going to use to go over the next 1/10 of a unit. So I'm trying to figure out ultimately what my velocity is after 0.3 seconds. So at t equals 0.2, my velocity we said was -1.9. If I go ahead and plug that in to this equation to figure out what the slope is, then v prime, the slope, is going to be -1.9 minus 10. So this is 1.9 minus 10, or -8.1. So the slope I'm going to use between this next two is -8.1. So the slope, this first line had slope -10. This second line had slope minus 9. This third line has slope minus 8.1. Each of these lines is a little less steep than the one before it. So if I move down the slope 8.1 for 1/10 of a unit, by how much do I drop? What's minus 8.1 times a tenth times 0.1?
Minus 0.81.
Yes, minus 0.81. I drop by another minus 0.81. So from here to here is minus 0.81. And if I start off at height negative 1.9 and I drop by another negative 0.81, where am I? What height am I here?
Negative 2.71.
Negative 2.71. Where did I get the minus 2.71? Well, I started off at height minus 1.9. I moved over by negative 0.81. Sorry, I'm going down by slope negative 0.81 for a distance of 0.1 unit. That's another negative 0.81. So negative 0.81. If I drop by negative 0.81 and I started off at negative 1.9, I'm going to be at negative 0.271. Let's just do one more. Let's figure out where we are after 4/10 of a second. So right after 3/10 of a second, I'm at height negative 2.71. That's my velocity, negative 2.71 meters per second. So let's figure out where we are at 4/10 of a second. So t equals 3/10 of a second. My velocity supposedly is minus 2.71. We plug that in to find out what b prime is. So negative 2.71 minus 10 is 2.71 minus 10, or what, negative 7.29. Obviously, I'm accumulating digits which are not really significant, but I'm going to write them anyway, just so I don't confuse you. So if I move over with a slope negative 7.29 by 0.1 units, then I'm actually dropping another negative 7.29 times 0.1. In other words, minus 0.729 units. That's by how much more I'm dropping in terms of my speed. Oops. And I started off at, where was I? Negative 2.71. If I subtract off another 0.729, what do I end up with? Minus 3.439, something like that. you can see what you're creating here. You're approximating that curve that we knew we were going to get. Now, these points don't lie exactly on this curve. Actually, the curve probably above those points. They have approximately the same shape, but they don't really lie on the true curve. Why not? Because what we're doing is we're following these straight line segments. We're assuming that the slope doesn't change between 0 and 0.1. We're making just one jump from 0 to 0.1, but the slope does change. As we move down, this is perennially changing. And so these points don't lie exactly on this curve. They're close to it for a while, and then they sort of drift away. If we want to get closer to the true curve, what we do is, instead of chopping it up into 0.1, a 0.1 mesh, we chop it up into a finer mesh. It's more work, but it gives you more accuracy. Is this making sense? Awesome. Okay, good. Good. So I deliberately didn't give you any fancy formulas the way I would have if this was a class in differential equations. In differential equations, we say, okay, well, the next point is going to be this number plus this number minus that number, and you just have to plug things in. And I confess that in a sense, it would be easier if I just gave you a formula, but it wouldn't be as intuitive. I mean, all we're doing is using these, what this is called a piecewise linear function. It's just little bits of lines stuck together to approximate a true curve. And the most important thing about this is that we've taken time, which is really a continuous variable, and we've artificially chopped it up so that we could approximate a solution to a differential equation, even when we couldn't get an exact solution to that differential equation. The finer you chop it up, the more work you have to do, but the closer this piecewise curve hangs around to the true curve. We may not always know what the true curve is. In this particular case, we have analytic techniques that help us find the true curve if we wanted to go to that effort. But in many cases, not only do we not have techniques, but techniques are not known. Solving differential equations, let me just make a meta point here.
One question.
Oh, yeah, please.
So you said the time block, the time intervals that you select, it would kind of it would determine the accuracy of it. Does that accuracy remain constant throughout it, or does it that accuracy slowly drift apart depending on?
So no matter how fine you chop it up, you're going to drift away from the true curve after a while. The finer you chop it up, the longer you sort of hang around the curve, but eventually you'll lose it. So if I wanted to go to if I wanted reasonable accuracy to like 3 seconds out, I'd have to chop it up to a certain amount. If I wanted that same accuracy to like 6 seconds out, I'd have to chop it much finer.
Okay.
Yeah, that's a great question. But I want to make a sort of a general point about solving differential equations exactly. Which again, if you've done a course in differential equations already, then you've done some of this. And if you haven't, then you probably will at some point in your career. But let me just go back to something like from Algebra 1. I promise I'm not trying to insult your intelligence here. I'm just trying to make a point. So how do you solve this equation?
Subtract 3 on both sides.
Subtract 3 from both sides, right. If the equation is built with pluses, you're going to do the inverse operation minus to solve the equation. Let's say I give you 3x equals 6. How are you going to solve this equation?
Divide by 3.
Yeah, divide both sides by 3. If the equation is built by multiplication, then you use the inverse operation division to solve it. What if I give you something like 2x plus 3 equals 9? Now let's make it 11. 2x plus 3 equals 11. Now there's two operations there, and you're going to slowly unpack the thing. My daughter right now, my youngest daughter is in pre-algebra, and we keep saying how, X is like the candy, and it's wrapped up, in this case, in a couple of wrappers. And so you have to undo the wrappers from the outside in. So to undo your addition, you subtract 2x equals 8, and then we have an inside wrapper, which is multiplication by 2. So to undo that wrapper, you divide by 2, and so x equals 4, and now you have the candy, and you can eat it. So whenever you use an operation to build an equation, you have to use the inverse operation to unpack the equation. It's like that with differential equations too. So if I have something like b prime equals v, or whatever it is, whatever the differential equation is, because it's a differential equation, by definition, you use derivative to build it. There's the derivative. So if derivative is used to build the equation, what technique, what do you need to undo that? What undoes derivative?
Integral.
Yeah, integral. Every single technique you learn in differential equation involves integrals. The reason they do that is because you're undoing derivative. So to solve it, to solve a differential equation, you need integrals. That's not a surprise. It's the same reason I need division and subtraction to solve that equation. You always need the inverse operation of whatever you use to build the differential equation. And those of you who are veterans of Calculus 2, which I think are all of you, know some, what? Okay, know some annoying, interesting facts about integration. You know that you can write down the derivative of basically any function I can write down. With the product rule, quotient rule, chain rule, whatever, pretty much anything you can write down, it's derivative. But there are many integrals which can't be evaluated in terms of elementary principles. I mean, there are plenty that can, but there are more that can't. One of the easiest ones, one of the first ones you ever see is this, e to the x squared. It's a perfectly nice function, and it has a perfectly nice integral. But the antiderivative of this cannot be written down in terms of anything you would recognize. So the antiderivative cannot be written in terms of elementary functions. Elementary functions, things like plus, minus, times, divide, polynomials, rational functions, sines, cosines, exponentials, logarithms. There's no combination of these things, no finite combination of these things, which will allow us to write down the antiderivative of that. And that's just the way things are with antiderivatives. They're most functions, after you get from the very basic ones, I mean, you can write down the antiderivative of any polynomial. After calculus 2, you can write down the antiderivative of any rational function. You can write down the antiderivative of sine and cosine of, e to the x. But if you start putting these things together in any sort of complicated way, e to the x squared or whatever, there's no way to write down the antiderivative in terms of anything you would recognize. I mean, if I wanted to write down the antiderivative of e to the x squared times x, that's easy. That's just a u substitution problem. This one is not only hard, it's impossible. It's not like, I'm not talking about the current state of mathematical ignorance. We can prove that you cannot write the antiderivative of that down in terms of elementary functions. That's something that can be proven. So we have this sort of pair of uncomfortable facts, the first of which I've erased cleverly, which says that to solve a differential equation, you need antiderivatives, you need integrals. And secondly, many integrals can't be evaluated in terms of elementary functions. Many antiderivatives of elementary functions can't be written down in terms of elementary functions. So we have this sort of gap. A lot of these problems we can't do analytically. It just can't be done. So these approximation techniques, like over here, these become very important. Now, this clearly was more complicated or harder to understand the first time than I intended it to be. But basically, all you're doing is sort of starting at a given point, following the slide down a straight line, figuring out what the slope is for the next time, following that down, figuring out what the slope is for the next time, following that down. So if I had broken this down into a mesh that was half as wide as this, I would have only slid down this first one so far, and then the second one would have had a different slope because I'd recompute there, and then I'd recompute here, and I would have stayed closer to this curve for longer. Sooner or later, I'm going to drift away again, but I would have stayed closer to that curve for longer. More work, more accuracy. How do you feel? Is the basic idea there? Awesome. In that case, have a great weekend.